This video is a step-by-step solution for the example entitled Determining Entropy Production in Heat Pump Components. In this example, you will learn about analyzing a series of processes for refrigerant 22 across multiple control volumes forming a closed cycle at steady state. In this example, you will learn to compute the rate of entropy production across the control volumes and determine the source of irreversibility on these respective components. Let's take a look at the problem statement as given to us. Components of a heat pump for supplying heated air to a dwelling are shown in the schematic below. At steady state, refrigerant 22 enters the compressor at 25 degrees C and 3.5 bar, and is compressed adiabatically to 75 degrees C and 14 bar. From the compressor, the refrigerant passes through the condenser, where it condenses to a liquid at 28 degrees C and 14 bar. The refrigerant then expands through a throttling valve to 3.5 bar. The states of the refrigerant are shown in the accompanying TS diagram. Return air from the dwelling enters the condenser at 20 degrees C and 1 bar with a volumetric flow rate of 0.42 cubic meters per second and exit at 50 degrees C with a negligible change in pressure. Using the ideal gas model for the air and neglecting kinetic and potential energy effects, A. Determine the rate of entropy production in kilowatt per Kelvin for control volumes enclosing the condenser, compressor, and expansion valves respectively. And B. Discuss the sources of irreversibility in the components considered in Part A. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red for the information provided, we have the following. Components of a heat pump for supplying heated air to a dwelling are shown in the schematic below. At steady state, refrigerant 22 enters the compressor at 25 degrees C and 3.5 bar and is compressed adiabatically to 75 degrees C and 14 bar. From the compressor, the refrigerant passes through the condenser where it condenses to a liquid at 28 degrees C and 14 bar. The refrigerant then expands through a throttling valve to 3.5 bar. The states of the refrigerant are shown in the accompanying TS diagram. Return air from the dwelling enters the condenser at 20 degrees C and 1 bar with a volumetric flow rate of 0.42 cubic meters per second and exit at 50 degrees C with negligible change in pressure. Using the ideal gas model for the air and neglecting kinetic and potential energy effects. And highlighted in green for the requested information we have, A. Determine the rates of entropy production in kilowatt per Kelvin for control volume enclosing the condenser, the compressor, and the expansion valve. And B. Discuss the sources of irreversibilities in the component considered in Part A. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement presented here in a bulleted list format. Refrigerant 22 is compressed adiabatically, condensed by heat transfer to air passing through a heat exchanger, and then expanded through a throttling valve. Steady-state operating data are known. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement, presented again as a bulleted list. Determine the entropy production rates for control volumes enclosing the condenser, compressor, and expansion valve, respectively, and discuss the sources of irreversibility in these components. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help in developing our solution. The first thing to note is that there is mass entering and leaving the various components. This immediately suggests that a control volume approach is the correct one for each of the components. Having recognized this key fact, let's select our control volume boundaries. In our case, the control volume boundaries are selected to enclose the various components and will be delineated on a schematic with red dashed line. Specifically, we have a control volume around the compressor, tying in the specified inlet and exit condition, the condenser with its specified condition on both sides of the heat exchanger, the refrigerant on one side, and the air on the other side with its specified volumetric flow rate, and the expansion valve with its specified exit condition. The next step is to develop the appropriate thermodynamic diagram to represent the processes. In this case, the TS diagram was provided to us. Let's highlight the diagram with the information provided. State 1 is a superheated vapor state at a given pressure of 3.5 bar, and its temperature value is given to be T1 is equal to minus 5 degrees C. The process from 1 to 2 is a compression process to a given pressure P2 equal 14 bar and a given temperature T2 equal to 75 degrees C. The process is an actual compression process represented by a dashed line veering to the right on the TS diagram, indicative of a specific entropy increase for this process. The process from 2 to 3 is a cooling process at constant pressure. The process followed the isobaric line at 14 bar, first in the superheated region until we reach the saturated vapor state on the right side of the vapor dome at a temperature corresponding to the saturation temperature at that pressure. Then the refrigerant condenses at constant temperature through the vapor dome. Once we reach the saturated liquid state on the left side of the vapor dome, the cooling process continues to a subcooled or compressed liquid state for state 3 at a given temperature of 28 degrees C. Next, the process from 3 to 4 is a throttling process. The process is represented by a dashed line veering to the right on the TS diagram until we reach state 4 at a lower pressure and temperature as compared to state 3. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. Each component is analyzed as a control volume at steady state. The compressor operates adiabatically, and the expansion across the valve is a throttling process. For the control volume enclosing the condenser, W dot is equal to 0 and Q dot is equal to 0. Kinetic and potential energy effect can be neglected. And finally, the air is modeled as an ideal gas with a constant Cp equal to 1.005 kilojoules per kilogram Kelvin. Having completed all the preliminary steps for our solution and represented the processes on the TS diagram, let's develop the rest of the analysis. For part A, let us begin by obtaining property data at each of the principal refrigerant states located on the schematic and TS diagram. At the inlet of the compressor, the refrigerant is superheated vapor at minus 5 degrees C and 3.5 bar. From the superheated vapor table for refrigerant 22, we obtain S1 is equal to 0.9572 kilojoules per kilogram Kelvin. Similarly, at state 2, the refrigerant is superheated vapor at 75 degrees C and 14 bar. Interpolating in the table gives us S2 is equal to 0.98225 kilojoules per kilogram Kelvin, and H2 is equal to 294.17 kilojoules per kilogram. State 3 is given to be a compressed or subcooled liquid at 28 degrees C and 14 bar. From the temperature-based saturation table for refrigerant 22, S3 is approximately equal to S sub F at 28 degrees C, which is equal to 0.2936 kilojoules per kilogram Kelvin. And H3 is approximately equal to H sub F at 28 degrees C, which is equal to 79.05 kilojoules per kilogram. The expansion through the valve is a throttling process, so H3 is equal to H4 by virtue of the energy rate balance and the fact that the expansion valve is a strictly passive component with no work or heat transfer exchange with the surroundings. Using data from the pressure-based saturation table, the quality at state 4 is given by X4 is equal to H4 minus HF4 divided by HFG4, which gives us a mixture quality of X4 is equal to 0.216. Next, we obtain the specific entropy as follows. S4 is equal to SF4 plus X4 times SG4 minus SF4. Substituting numerical values from the table, the specific entropy at state 4 is then determined to be S4 is equal to 0.3078 kilojoules per kilogram Kelvin. Now let's consider the control volume enclosing the condenser. With respect to assumptions 1 and 3, the entropy rate balance reduces to 0 is equal to m dot refrigerant times S2 plus S3 plus m dot air times S5 plus S6 plus sigma dot for the condenser. Evaluating sigma dot condenser requires two mass flow rate m dot air and m dot refrigerant, as well as the change in specific entropy for the air. These are obtained next as follows. The mass flow rate of air is evaluated using the ideal gas model and the known volumetric flow rate and the state parameter. m dot air is equal to AV5 times P5 divided by R times T5. Substituting the given numerical parameter values and calculating the ideal gas constant for air as the universal gas constant per mole of gas divided by the molecular mass of air, and paying special attention to the unit conversions from bar to Newton per meter squared and joules to kilojoules allows us to evaluate the mass flow rate of air as follows. This gives us a value of m dot air is equal to 0.5 kilograms per second. Next, we could determine the refrigerant mass flow rate by doing an energy balance for the control volume enclosing the condenser, together with the assumptions 1, 3, and 4. This yields the following. m dot refrigerant is equal to m dot air times H6 minus H5 divided by H2 minus H3. With the use of assumption 5, the enthalpy change for the air can be evaluated as follows. H6 minus H5 is equal to Cp times T6 minus T5. Substituting the numerical values, we get the following expression, which gives us a numerical value for the refrigerant mass flow rate of m dot refrigerant is equal to 0.07 kilograms per second. Using the equation for the change in specific entropy for a gas with constant specific heat, the change in specific entropy of the air is given by the following expression. S6 minus S5 is equal to C sub P times log of T6 over T5 minus R times the log of P6 over P5. Substituting numerical value gives us the following expression, where the last term drops out as the pressure does not change between states 5 and 6. The specific entropy change for the air is then determined to be S6 minus S5 is equal to 0.098 kilojoules per kilogram Kelvin. Finally, solving the entropy balance in the condenser for sigma dot of the condenser gives us the following expression. Sigma dot condenser is equal to m dot refrigerant times S3 minus S2 plus m dot air times S6 minus S5. Substituting the numerical value gives us the following expression. And the entropy production in the condenser is then calculated to be sigma dot condenser is equal to 7.95 10 to the minus 4 kilowatt per Kelvin, which is the first answer we were seeking. Now, for the control volume enclosing the compressor, the entropy rate balance reduces with assumption 1 and 3 to the following. 0 is equal to m dot refrigerant times S1 minus S2 plus sigma dot of the compressor. Solving for the entropy production in the compressor, we get sigma dot compressor is equal to m dot refrigerant times S2 minus S1. Substituting the numerical values and evaluating the expression, we get the following, giving us an entropy production in the compressor of sigma dot compressor is equal to 17.5 10 to the minus 4 kilowatt per Kelvin, which is the second answer we were seeking. Finally, for the control volume and closing the throttling valve, the entropy rate balance reduces to 0 is equal to m dot refrigerant times S3 minus S4 plus sigma dot of the valve. Solving for the entropy production in the valve and substituting the numerical values, we get the following, giving us a value for the entropy production in a throttling valve to be sigma dot valve is equal to 9.94 10 to the minus 4 kilowatt per Kelvin, which is the third answer we were seeking. For part B, the following table summarizes from the largest to the smallest the calculated entropy production rates in the three components considered. The values range from 17.5 10 to the minus 4 kilowatt per Kelvin for the compressor to 7.95 10 to the minus 4 kilowatt per Kelvin for the condenser. In the compressor, the sources of entropy production are due to the fluid friction, mechanical friction of the moving parts, and the internal heat transfer. As for the valve, the irreversibility is primarily due to the fluid friction accompanying the irreversible expansion across the valve. In the case of the condenser, the principal source of irreversibility is the finite temperature difference between the air and the refrigerant streams. In this example, there are no pressure drops in either stream passing through the condenser, but slight pressure drops due to fluid friction would normally contribute to irreversibility of the condenser, which would contribute to additional entropy production. Note that the evaporator shown in the schematic has not been analyzed. In closing, I would like to make a few remarks on the analysis we just conducted. Due to the relatively small temperature change of the air, the specific heat C sub P can be taken as constant at the average of the inlet and exit air temperatures. Temperatures in Kelvin are used to evaluate m dot refrigerant, but since a temperature difference is involved, the same result would be obtained if temperatures in degrees C were used. However, temperatures in K, not degrees C, are required when a temperature ratio is involved, as in the specific heat equation used to evaluate S6 minus S5. By focusing attention on reducing irreversibilities at the site with the highest entropy production rates, thermodynamic improvements may be possible. However, costs and other constraints must be considered, and those can be overriding. Quick quiz. If the compressor operated adiabatically and without internal irreversibilities, determine the temperature of the refrigerant at the compressor exit in degrees C, keeping the compressor inlet state and exit pressure the same. You may want to stop the video at this point and work on the answer. The answer is 65 degrees C. Hopefully, this is the answer you obtained. If not, review carefully the steps in this video, particularly for computing the entropy production in the compressor, and check your calculations and properly look up in the tables. If you are still having trouble getting the correct answer, here are a few hints. If the compressor operates adiabatically and without irreversibilities, it also operates isentropically. Hence, S2S is equal to S1 is equal to 0.9572 kilojoules per kilogram Kelvin. This specific entropy value falls between two temperatures in the table of properties of superheated refrigerant 22, namely 60 degrees C and 70 degrees C. The temperature at the exit of the compressor, T2S, can be obtained by interpolation. The numerical answer is left as an exercise. Note that the temperature T2S corresponding to an isentropic compressor is lower than the temperature T2 specified in the original example. In closing, in this example, we have learned about analyzing a series of processes for refrigerant 22 across multiple control volumes, undergoing a cycle at steady state. We learned how to compute the rates of entropy production across the various components and determine the sources of irreversibilities in those respective components. This concludes the step-by-step solution of the example entitled Determining Entropy Production in Heat Pump Components.